All right, let's get right into it. We're about to explore one of the most mind-blowing ideas in the history of computing. Seriously, it's the moment we figured out how to teach a machine what a word means. Not just how to spell it, but to understand it so well that you can literally do math on abstract concepts. This is the story of how AI learned to do math with words. So, let's start with what seems like an impossible question. How would you even begin to do this? Think about it for a second. How do you take a feeling like love or a concept as complex as democracy and boil it down to a list of numbers? For decades, this question was a total brick wall. It was the one thing holding us back from creating machines that could truly understand us. And to really see why this is so tough, just look at this simple sentence. When I say I went to the bank, am I talking about a river bank or a money bank? You and I know the difference instantly, right? It's all about context. But for a computer which thinks in pure, cold logic, this is a complete nightmare. Language is just drenched in this kind of hidden meaning. And the problem goes way deeper than that. For computers, language is basically a minefield. You've got ambiguity, like our bank example. You've got context. If I say, it's hot in here, am I just stating a fact or am I asking you to open a window? Then there's sarcasm, where we mean the exact opposite of what we say. And don't even get me started on long-range dependencies, where a computer needs to remember who or what we were talking about paragraphs ago. For a very long time, these problems made real language understanding feel like pure science fiction. So, what was the first big idea to try and crack this code? Well, the engineers took an engineer's approach. They decided to treat words not as rich concepts, but as simple on or off switches. A really straightforward idea that, as we're about to see, was deeply flawed. This method is called one-hot encoding. The idea is pretty simple. Imagine a giant control panel with a light switch for every single word in the dictionary. Cat gets a switch, dog gets a switch, car gets a switch. To represent a word, you just flip its own personal switch to 1 and make sure every other switch is set to 0. It's a unique ID for every word. Simple, clean, but it has a fatal flaw. And here's what that looks like in math terms. Cat is a 1 in the first spot, with zeros everywhere else. Dog is a 1 in the second spot, car in the third. From a computer's point of view, these lists of numbers are totally separate. They have nothing in common. They're just lonely points in space that have no connection to each other whatsoever. And this is where the whole thing just falls apart. When you ask the computer to calculate how similar cat and dog are, the math says 0. Nothing. No relationship. And when you ask it to compare cat and car, you get the exact same answer, 0. The computer literally believes that a cat is just as unrelated to a dog as it is to a car. This whole system has no concept of meaning at all. It's like having a dictionary with no definitions. Then, in 2013, everything changed. A team of researchers at Google came up with a completely revolutionary idea. They said, what if words aren't individual switches? What if instead they were all points on a giant complex map, a map of meaning itself? This idea is called a word embedding, and it is so elegant. Instead of giving each word a unique ID, you give it a coordinate, a specific address in this huge multi-dimensional space. The one beautiful rule is this: words with similar meanings are placed close to each other. It's like building a constellation of ideas, where cat and dog are neighboring stars, but car is often a completely different galaxy. So what does that actually look like? Well, check out these new vectors. The numbers aren't just ones and zeros anymore. Now they represent abstract qualities. So maybe that first number represents size, the second is fluffiness, and the third is how mechanical something is. All of a sudden, you can see that the numbers for cat and dog are pretty similar, right? But the vector for car is completely different. The computer can finally see the relationship in the numbers. And the results are just wow. When we run the math now, the similarity score between cat and dog is super high, let's say 0.80, but the score between cat and car is really low, maybe 0.18. For the very first time, the math actually reflected reality. The machine finally understood that cats and dogs are related concepts. This was the moment meaning finally entered the machine. This incredible new power led to one of the most famous, most mind-bending demonstrations in the entire history of AI. It was proof that this space of meaning wasn't just a random map. It had a hidden logic, a structure that you could navigate with something as simple as high school algebra. This right here is the equation that absolutely shook the world of AI. It says that if you take the mathematical representation for king, Subtract the representation for man and then add the representation for woman, the answer you get is incredibly close to the representation for queen. This is algebra on concepts like royalty and gender. It is just extraordinary. So how does the magic work? Think of it like giving the computer directions on a map. You start at the location for king. Then you move away from the idea of man. You're basically removing the concept of maleness. From that new point, you travel in the direction of woman, adding the concept of femaleness. And where do you end up? Right next door to queen. And here's a super simplified look at the actual numbers. Let's say we have dimensions for royalty and gender. King is high on royalty, but low on female gender. When you subtract man and add woman, look what happens to that gender number. It flips from 0.1 to 0.9, while royalty stays high. The final vector is a perfect mathematical description of a queen. It's not magic, it's just math. Okay, so this is a really cool math trick from back in 2013. But why are we talking about it now? Why does it matter so much? Because this discovery wasn't just some academic paper. It was the key that turned the ignition on the entire generative AI revolution that we are all living through right now. Let me be absolutely clear about this. Without the ability to turn words into these meaningful number vectors, without word embeddings, there would be no ChatGPT, no large language models, none of it. This idea, giving a computer a sense of what a word actually means, is the absolute bedrock that all of modern AI is built on. You can draw a straight line from that initial spark. In 2013, Word2Vec proved that meaning could be turned into math. That breakthrough enabled the creation of the transformer architecture in 2017, which finally solved that pesky context problem we talked about earlier. And that, in turn, led directly to the explosion of generative AI we see everywhere today. It all started right here. So, what's the big takeaway from all of this? The huge leap forward for AI wasn't about faster computer chips. It was about this brand new idea, turning words into coordinates on a map of meaning. This is what allows computers to use simple math to understand really complex relationships. That king minus man plus woman equals queen equation was the jaw-dropping proof that it worked. And that single discovery is the direct ancestor of the AI tools you probably use every single day. And that leaves us with a final, massive question. For the very first time in human history, we have translated a fundamental part of our experience, the meaning of our language, into the native tongue of the machine, mathematics. We gave them a key to our world, a way for them to navigate the universe of our ideas. We taught them what our words mean. So the question is, what do we teach them next?